Okay, this video is part 2 of the enzyme video, and this is Mr. Dundon. Thanks for watching, and hopefully you learned something. So I'm just going to create a new slide just after I explain that this is all about how pH, temperature, and chemical inhibitors can alter the binding of enzyme and substrates at the active site. We really have 3, but I like to think of 4 or even 5 factors that can affect enzyme activity and how quickly or slowly the reaction rate happens. And I remember it by using this. That pig is crazy. So that's a little acronym that I use to remember that we have temperature, pH, inhibitors, and either concentration of either the enzyme or the substrate, and cofactors. So these are the main ones, these first 3, but this is that additional information that is going to separate the A+ students and just the regular students. So we're going to go through each one of these in detail, and hopefully you can use this in your next test. So temperature affects reaction rates in 2 ways. Firstly, the temperature is responsible for the initial kinetic energy of the substrate and the enzyme. So if we draw a closed system here, we're going to have substrate molecules that I'm going to draw as these little black circles. And if we didn't have an enzyme, these molecules are going to collide into one another, and if they have enough energy and hit in the correct orientation, we're going to have a reaction. So how does temperature relate to this system? Well, as temperature increases, we have more kinetic energy. So more temperature, more kinetic energy, which therefore increases the probability of collisions and therefore reactions. So if we throw some enzymes in there as well, I'll do them in red. So red enzymes. Okay. If we increase the temperature, we're going to increase the kinetic energy of both the enzyme and the substrate. They're going to collide more often, and therefore, if they're colliding, we're going to have increased collisions and therefore increased reactions. So that's a good thing. However, enzymes are very, very susceptible to changes in temperature. So I like to show this by drawing a graph. So if we have reaction rate over here on the y-axis, so if we have reaction rate over here on the y-axis, and on the bottom we have temperature, what happens as we increase temperature, substrate and enzyme hit more often, they're going to react faster, so we're going to have an increased reaction rate. More collisions, more reaction. However, if the temperature increases too much, we get no reaction at all. So what is the difference that's happening here in A compared to here in B? Well, in A, all that's happening is that temperature is causing increased kinetic energy, increased probability of collisions, therefore reaction rate goes up. However, at a certain temperature, we'll call this the optimum temperature. We have the most collisions, the most reactions between the enzyme and substrate. Reaction rate is at its highest, at its peak. After that, the enzyme starts to break down. So the three-dimensional shape of our enzyme goes from that to now, let's say something like this. This enzyme over here is no longer going to be able to catalyze our reaction. So the reaction is going to stop. And the reason why that happens is because temperature will break our weak hydrogen bonds, which we know is really important to the structure of a protein. And that's what an enzyme is. So it's going to break these weak hydrogen bonds, and therefore we're going to have an altered 3D shape. Okay, so the 3D shape is going to change. So temperature is good in one way. If we increase the temperature, we're going to have faster and faster reaction rates, but there will reach a point where after that temperature increase, we're going to deform the three-dimensional shape of the protein, and we call that process, or the result of that, we say the enzyme has denatured. Okay, so temperature increases kinetic energy, increases the probability of collisions, but if we go too far, we'll denature the enzyme, and the active site will no longer be complementary to our substrate. pH is very similar. Okay, I like to draw that one with a graph as well. So if we have pH down here and reaction rate here, we're going to see this nice curve where this point here will be our optimal pH for that particular enzyme. Now, again, either side of the optimum, we're going to get decreased reaction rate, and that's because this is causing a change. So if we have change in pH, we're going to change our ionic bonding happening in the tertiary folding, the tertiary structure. So we're going to change the ionic bonding between the R groups, and therefore the active site will change. And that's not good. The more active site changes, the less it's complementary to our substrate, the less it can catalyze a reaction. It's not as severe as temperature. So as once temperature goes over a certain point, the hydrogen bonds just break apart and we lose the three-dimensional shape. As you can see, there will be some reaction on either side of the optimal pH, but it's going to reduce quite quickly. Now we might have an enzyme that has its optimal pH much lower, maybe say around 3, and we might have some that have an optimal pH around 7. This all depends on the enzyme and where it's advantageous to be active. So this particular enzyme might be active in the stomach, whereas this enzyme might be active in the blood. Okay, so pH is very important to have an optimal pH because it will affect the ionic bonding, which will change the active site, which will then make the substrate not complementary. Okay, inhibitors. We actually have two types of inhibitors. The first type of inhibitor is a competitive inhibitor, and the reason why it's competitive is because it competes for the active site. So if we have our enzyme, okay, our desired substrate might be this particular molecule, which we call A, and it normally can fit in the active site quite well and undergo its reaction to become, say, B or B and C, whatever the reaction dictates. However, we've got this other molecule that, let's call this molecule D, that also fits in there. However, this enzyme can't actually catalyze that reaction or breakdown of D. So D just sits in there. It competes for the active site, just sits in there, and then nothing happens. So it just basically clogs up the active site, or occupies the active site, and therefore we get a reduced reaction rate. Now they both have equal chance of filling up the active site. However, if we've got a lot of enzyme, a lot of substrate, and a lot of inhibitors, then some of A will go into some enzymes, some of D will go into the other enzymes, and then just clog it up. So we're really going to reduce the active site. Okay, so that's competitive inhibitors. They're competing for the active site, and then they're blocking up the active site. They're occupying the active site, so it can't catalyze the reaction. The second type is a non-competitor. Okay, a non-competitor or non-competitive inhibitor. So a non-competitor is going to not fill our active site. Okay, so remember this is our active site. So it's not going to fill our active site, but we actually might have a different area on the enzyme. So we might have something in this corner where we get a molecule joining here. So we get a molecule joining here, and that actually causes a change to the active site. So this non-competitive inhibitor binds, and it binds to an allosteric site. Okay, binds to an allosteric site, and it's not our active site, it's a different site, but it changes our active site. So now our active site is no longer complementary. So it's no longer complementary. Okay. The final two, I won't go into these in much detail, but basically, if we increase the concentration, okay, so if we increase the concentration of the substrate, so we'll just say concentration. If we increase the concentration of the substrate, eventually we'll saturate the enzyme, and therefore we'll plateau off. And we need, sometimes with enzymes, the presence of a cofactor, which will initialize the catalyzing reaction with an enzyme. Okay, so that's basically it. So remember, that pig is crazy, and hopefully you have some luck in your next test. If you need any extra help, please put them in the comments section, ask questions. If you want something explained in a little bit more detail, ask away, and I'll make another video. Make sure you like this video, subscribe, and have a great day. Take it easy.